Yes, so good afternoon, everyone. My name is Ioannis Athanasidis. I'm a professor of AI in Wageningen University and Research, and I'm also leading the work package on simulation intelligence in PHENET. And today I will give you a short introduction on AI in plant phenotyping and how we use it in PHENET. But yeah, I think just to kick off. Um, it is quite mind-blowing that AI has won two Nobel awards this year. One of them was about protein folding in chemistry, and I think the key question is how does it really work? So I will spend the first part of my presentation just to show you the basic principles of how machine learning methods are working. So until 15 years ago, traditional or data-driven AI machine learning was based on data that were coming together with labels. And then using starting from the data, the first step was to design some features, and then from these features build a machine learning model that could be using different algorithms, predict some labels, and then using teacher feedback, compare these predictions with the original labels and use this error to further tune the machine learning models. However, the main bottleneck in this way of working was the design and the selection of the right features, which was a challenge. There is when things changed about 15 years ago, when deep learning came into the game and introduced what is called representation learning, where we both combine the feature design and the model prediction in one deeper neural network construction. Again, the whole pipeline is the same, but now we have in one very complex or more complex model doing two tasks in one step, and that is both to design features and develop a prediction model. And these kind of models are using convolutions for machine vision or attention or transformers for language models. And this is what enabled the current development of artificial intelligence and many of the new methods that we see succeeding lately. It was this plus the fact that there were very big data sets collected with labels, tailored hardware for computation, and optimal software implementations. Until a couple of years ago, some very, very big companies, only a few of them, tried to break through on the problem of having data annotations by introducing a new generation of models called generative models that are able, instead of predicting labels, to predict the original data. So these models are different because they can generate raw data as those used for training. And that means that they don't need any longer teacher feedback. They don't learn them. We don't need to annotate labels. They learn from the input data. So to give an example, this is more like filling in the gaps. So if we have a sentence that says a magic wand, then these models are learning what is the next word, and then based on their predictions, being rewarded for when they're doing it right. And with this, and this is what kind of created a second wave of development in AI in the past couple of years with GPTs and all these generative models for creating images and text. And today, AI is transforming the way we are interacting with computers. And the key question that I will try to address today is, can we do the same in plant phenotyping, and in what extent? And Bertrand presented very well that we are in a, there are several global challenges that needs to be addressed. There are very, very many relevant problems related to food security, climate change, biodiversity, and we have big data, we have computational power, and we have a lot of experience in addressing those questions. The key challenge is how to bring them together. And there are a lot of methods from AI that have been directly applied into plant phenotyping and agriculture from remote sensing that about 20, 25 years ago started to be used for detecting vegetation density, water deficit, crop stress, to and nowadays also in PHENET we are developing it for detecting traits and giving advice to farmers, but also all kind of machine vision innovations for plant phenotyping that matured very much in the past 10 years, and from a toolkit that was in the back of some computers of a couple of hackers. Now it can be used in plant phenotyping facilities in a very large scale. So it looks like that with the abundance of environmental data, we can bring in machine learning and AI methods from the shelf to address global challenges like those that we're interested in. However, if we look under the hood, this is a recent paper that did a bibliographic analysis on how AI has been diffused across different scientific fields. And because these numbers are little small, let me blow them up for you. And we see that it had a very big impact in environmental sciences, in biology, but out of all these fields, the one that it had the smallest impact was agriculture and food. Even in philosophy, there were more papers related to AI in the past 20 years, or the increase was bigger in philosophy compared to agriculture and food. And this is a little bit of a teaser about why this is the case and what makes agri-foods different compared to other disciplines. And I think there are two dimensions. One is the data gap. This is a figure that shows how many data points are used to train notable AI systems. And I think you can see my mouse. So in the beginning, let's say 50 years ago, machine learning and AI was using data sets which was in the order of few hundred or thousands labels, and gradually it moved up in an exponential growth, and today concurrent AI systems are using trillions of labels. If we look into data that we have available in agriculture, agronomic trial data sets have are of size in the size of few hundreds, the biggest ones. If we look into breeding trials, maybe they are in the order of 50,000. And if we look into phenotypical trials, maybe we get into data sets in the order of millions if we're talking about annotated photographs of diseases and things like that, which kind of tells us that safely we can use technologies that are 20 years old and be on the safe side of things. The other thing is that despite all its success, AI can generate very nice images and text and so on, but then despite being trained with billions of images, still it hallucinates a lot. So it still creates images with more hands than necessary, like this ones. In most generated images, faces are not smiling because it gets it wrong with the details and the teeth and things like that. So it has a foundational limitation on how to deal with details. And this is where these two things kind of summarize my point. While this approach, sometimes it works, if we want to address global challenges, it's not going to work. And this is because we cannot waste all the knowledge we already have and expect to rediscover it from data, because we don't have a lot of data. And even if we do, it's not guaranteed that it will be rediscovered in the right way. And the other thing is because we're interested for future conditions where we have scale interactions and far too many uncertainties. So we need to correct for these things. And today I will show you a couple of examples on how we are trying to develop a new generation of tailor-made AI solutions that can help us build actionable, trustworthy systems to address some of these global challenges by including prior knowledge, but also by testing them thoroughly and benchmarking them so that we know that they are working correctly for the correct reasons. So the first one is to employ physics-informed neural networks for estimating crop heights. That's work we're doing with a PhD student here in Wageningen, where we employ a deep learning model to predict the height of different wheat cultivars. And here in the bottom, you see some results. And we do that not only by giving it teacher feedback from the observations, but also using the knowledge of the domain in the form of a physics laws that helps improve the training process of these deep learning models so that they produce physically plausible solutions. The second one is the work we are doing with GEM prediction, where we are working on the genome to field public benchmark. Here, this is one of the biggest public data sets for genome by environment interaction. And these are the results of the public competition that they held last year, where several methods of different types, like classical machine learning, linear mixed models, and deep learning methods have been used for overall yield prediction and environment-specific rankings. And if you see here, it looks like that deep learning is far away from the frontier of more classical methods, either classical machine learning or linear or mixed models. And if we look into environment-specific rankings, there is a huge gap between the frontier of the best models and what we can actually build with deep learning. And the key question is why? Why does it fail? And if it fails with such a big data set of almost 5,000 genotypes in 250 environments, how long can we wait until we have enough data to build trustworthy models in this case? The main problem here is that deep learning models, as we said before, they hallucinate. They are learning shortcuts. So similar to the image problem that if you put a cow on the sea, it will not detect it as a cow because it learns the correlations with the background. So because it's not in a green pasture, it's not a cow. Similarly, what we have in this GEM data is we have a very strong influence of the environment component. And this is why the deep learning models turn to learn this shortcut that estimates the effect of the environment, but fails to learn effectively the other components like the genotypic or the G-by interaction effects. And this is exactly what we did with Eike Potze, a PhD student of mine here in Wageningen, to build a deep learning model that is able to first disentangle these targets, and we do that with a linear mixed model, and then train a deep learning model on these blobs that is able to do a genomic prediction task, a yield forecasting task, and then based on those, learn also an interaction about the G/E residuals. And once these three components are learned, then we can recompose the predictions and make predictions in new genotypes, but also in new environments. And this kind of thing requires quite a systematic model development pipeline on evaluating different model architectures and how to build them. But once they are there, we were able to learn invariant representations of these G/E interactions and actually improve in both metrics, both in overall yield and within trial in new years and new hybrids with repeated locations. So this is a way where where I have shown how we can use prior knowledge and good practices from the domain together with AI advances for building trustworthy systems. Looking ahead, I think the key question is how we can onboard these technologies and how to climb fast the AI technology ladder, but not too fast to avoid hallucinations. So keeping a balance between introducing new technologies, but also benchmarking it is challenging. And to do that, I think it's very important that we need a different way of working together. We need an AI ecosystem that it starts from user-inspired research by identifying targets and involving stakeholders from the beginning, have benchmarking facilities where we can actually produce results and accelerate process. And this includes both physical facilities, but also digital facilities. Sharing and accessing ground truth data is key for AI development so that we can evaluate models and accelerate impact, but also build a community, trusted partnerships, and invest in people, skills, and in values. And with that, I would like to thank you very much and leave the floor back to you, Bertrand. Also, given the time, we are hiring 2 tenure track positions. So if you have any very brilliant people who want to join us in Wageningen to work on AI, ask them to send me an email. Thank you very much.